In this lesson, we are finally going to talk about shaders. And we already talked about shaders. And it's one of the most anticipating topic, one of the most demanding topic. Maybe you don't know anything about shaders. Do not worry, it's a beginner-friendly lesson. And we are going to learn everything you need to know. But actually, everything showing up on the WebGL render, what you are seeing right now on my screen, is made possible because of shaders. And we've been using shaders. By using 3GS materials, you are using shaders not made by you, but made by the community, by Mr. Do, by people like that, that show things on your screen, show things in the render, all right? But now we are going to create our own shaders. In this lesson, it's a big one, as you can see. We are going to learn what is a shader and why we need shaders. We are going to create our own very simple shader. We are going to learn the syntax. Yeah, we're going to start by creating a simple one and then learn the syntax from this very simple shader. And we are going to do some exercises because it's all about practicing. And the next lessons are also about doing exercises and practicing. So yeah, first, what is a shader? I will do my best to explain to you that. It took me months to understand really what is a shader, so I will really do my best to help you on that. First, it's one of the main components of WebGL. If you were to start WebGL on your own without any library, just native WebGL, well, it's one of the first thing you will have to do. You have to write your own shaders. If you want to, I don't know, show a triangle on the canvas, you have to do shaders. And you have to start with that, almost start with that. Yeah, and this is why WebGL is so damn hard. It's because you have to learn so much new things just to get a triangle on the screen. Yeah, it's more comfortable with 3GS. But anyway, we are going to learn them here. So, a shader is a program. All right, it's just like a JavaScript program or a C++ program or something like that. Right now, it's going to be a program. A shader is a program written in GLSL. All right, so it's a new language. You will have to learn a new language, indeed. This program is sent to the GPU that we do the work for the WebGL. All right, we've been talking about the GPU for quite a long time. And this program, those program actually, will do two things. It will position each vertex of a geometry. So it's about positioning a geometry. So you create a geometry. We will create a 3JS geometry, and the shader will position the vertex of that geometry on the render. And then there is another shader that will colorize each visible pixel of that geometry. We are going to explain each one of those two, all right, in details with drawings, with examples, and play with those examples. So maybe you didn't understand yet. Do not worry, we're going to explain. I've been talking about pixel, like colorizing each visible pixel of that geometry. But pixel isn't accurate because pixel is about the screen. All right, it's about a unit in your computer, in your screen computer. It's not exact because sometimes you can have a render that is not even showing up on the screen. It's not in a canvas, and sometimes it's bigger but then scaled down, stuff like that. So it's not correct to say pixel. From now, we are going to talk about fragments. All right, fragments are like pixels but for the render. Right. The idea is that we send a lot of data to those shaders. We send data like the vertices coordinates, all right? Because if we want to position the vertices of a geometry, we have to provide those data. We send the data like the mesh transformation, so that if the mesh transformation, there is a position x equal 1, well, every vertices is supposed to move on the right or the opposite. Or if it's a rotation, well, every vertices will be impacted by this transformation. So we send the coordinates of the vertices, the mesh transformation, but also information about the camera. Because if you look at an object and then your camera turn on the left, we didn't move the object, but because we turned the camera, we rotated the camera on the left, well, this object is supposed to be on our right. And this is exactly why we need to send camera information. Just like if we are going to send data like the field of view of the camera, Because if the field of view is small, the object will look bigger on the render. And the opposite, if your field of view is very large, so it's more vertically, so very large, the object will look small once it's on the render. We can send many other data like colors, one for each vertex, maybe one for the whole geometry. We can send textures, we can send light so that we can do like a mathematics to make this part of the sphere brighter because there is a light over there. We can send data like fog, and we can send any data, random value, things like that. And we're going to use stuff like matrices, you will see. Then the GPU will process all of this data and follow the shader instructions. All right, the program we wrote in GLSL, the shader, is going to take those data and do stuff so that at the end, we position the vertices on the screen and we colorize each visible, not pixels, each visible fragment. That's the idea. If for now you're following me, great, you've been like 10 times faster than me when I first learned. There are two types of shaders, as you can hear. We've been talking about positioning the vertices and then colorizing each visible pixel of the geometry, each visible fragment of the geometry. I will say pixel and fragment, my bad. So yeah, let's start with the vertex shader. So, as we said, two types of shader, the vertex shader, and then later it's going to be the fragment shader. Learn that, it's the base. Vertex shader and then fragment shader. The vertex shader will position each vertex of the geometry. All right? So the idea is that we create the vertex shader, we send that shader to the GPU, but with a bunch of data. And it's the data I said earlier, like the vertices coordinates, the mesh transformation, camera information, stuff like that. And the GPU will follow our instructions inside the shader to position the vertices on the render. So let's go, let's do some drawings because it's always easier when we do drawings. So I'm going to use, I don't know, maybe, let's say orange for the vertex shader. So we have, my bad, it's never the right one. Ah, yeah, like this. So we have information. We send like, I don't know, a bunch of information like vertices, mesh position, stuff like that. I will use different color, why not? So vertices, this one is going to look like that, this one is going to look like that. These are datas. It's just data, coordinates, mesh information, camera information, stuff like that. And we send a bunch of data. Then we provide also a shader. So it's a vertex shader. We're talking about vertex shader. So the vertex shader is going to be some line of code. We are going to learn how to do that. And it will look something like that, like that, like that. All right, this is the... it's so hard to do like straight line. Like that. All right. This is the vertex shader, and I will write vertex. In those data, we provide position of the vertices, all right, and other things like the mesh transformation. In this vertex shader, we handle those, and we position at the end the vertices on the screen. It's not exact because it's not the string, it's more like on the render, all right? And it's on the fragments of the render. So for now, we are just going to draw a triangle. At the end, it can be a sphere, it can be many things, but the most simplest shape we can have is a triangle. And then because the camera is like that, the object transformation is like that, and the coordinates of the vertices are like that, we get, I don't know, something like one here, and one, I don't know, maybe here, like that. And that's all. We just position the vertices by using our vertex shader, all right? Vertex shader, here we have data, like this, and at the end we position things on the vertices. So it goes like this, and then like this, and we position things. So these are the vertices of our triangle. For now, we cannot see anything. All right, we just cannot see anything. It's just theoretical positions. All right, let's get back to the slides. We are missing some stuff here, but you will see. The same vertex shader, so that program, will be used for every vertices. All right, it's the same program that will be used for every vertices. So this program will be used to position this vertex, then this program for this vertex, and this program for this vertex. If you have thousands of vertices, the same program will be used for each of them. And this is the strength of the GPU, to be able to do thousands of things in parallel, but it's the same thing. But obviously, some data like the vertex position will be different for each one. All right, there will be data that are the same for all, like the camera position. It's the same for all the vertices. But the vertex position, which is this one, will be different. All right, so it's the same program, but there is a small part that will be different. Maybe it's going to be this one. All right, and this is going to be the vertex. Sorry, the vertex position. Yeah, that's it. Those type of data that change between each vertex are called attributes. And we're going to learn a lot of keywords. We learn vertex shader, fragment shader, and now we learn attributes. It's when you have a data. So this program will be used for each vertex, and there is a data that which will change between those because they are not at the same position, they are at different position. And obviously this data is the position, and this is called an attribute. And we will send different attributes. And actually we already did that. We already did that with the particles. Remember the particles? At a point we decided to have a different color between each vertex so that we get different color particles. We provided an attribute. It's a value that is different between each vertex. All right, cool. Let's move forward. So attributes, remember this one. Some data like the position of the mesh are the same for every vertices. Because when you want to render these triangles, it's inside so an object, and this object has a position. So maybe the position is a little on the right, so the triangles won't be here, they will be somewhere like, I don't know, over there, right? It's going to be this one. In our case, we're going to keep it in the center. So there is data that doesn't change between each one, like the position, like maybe a color, because it's an object that will look, I don't know, red, orange, or something like that, or green. The camera position, because the camera position, it's the same. We don't change the position of the camera between each vertex. And those type of data, we call those uniforms. And in our code, we are going to retrieve those data uniforms. I don't know, maybe put it there, like that. And then we will use those data to position things here. Attributes, uniforms. Attributes different between each vertex. Uniform, the same for every vertex. And we see that also the fragments. We are going to show that later. Anyway, more about uniforms and attributes later. We did so that now because I need you to know those words and how we use them inside the program. Once the vertices are placed by the vertex shader, the GPU knows what pixels of the geometry are visible and can proceed to the next shader, which is the vertex shader. So because everything is placed on the render space, on our 2D space, which can be the screen, where now look at this, our GPU knows which part of the geometry are visible, like that. So it's so hard. And the GPU will use the next part, which is the fragment shader. So it's the next shader to color each visible pixel of the geometry, because the GPU knows what are the visible part of that geometry because the vertices are now well placed. So the same fragment shader will be used for different visible fragments of the geometry. The idea is that we are going to write another shader. It's going to be a fragment. It's also GLSL, fragment, like that. And we are going to write the same kind of things. We are going to learn what to write inside of those. And we are going to write things like that, like that, like that, like that. So it's lines of code, as you can see. I don't know if you understood that. And yet again, we can provide data. All right, it can we can also have like I don't know, let's do data like this, and it's not exactly the same. Let's start with just the same one, so the uniform. So this was an attribute. I'm going to write attribute, just attribute, because I don't have room. And this one was a uniform. Uniform. And yet again, we can have uniform, but no attributes. All right, so this is a uniform, and we can get, I don't know, this uniform here in our code, and then use that uniform inside of our fragment shader. So we provide data. We provide the same data actually, but you will see. And then we use that fragment shader to use those data to colorize each pixel. So this one will look like this one will look like this, 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 and we colorize everything. And then we can see our geometry on the screen. And it's exactly what's happening here. The vertex shader position each vertex of our plane. So it's 2 triangles, so it's something like 4 vertices. It's actually 6, but anyway. And then the fragment shader, it's a very simple fragment shader that said, all right, everything is black. Every visible pixel is going to be black. Sorry, why did I say black? White. So the idea is the same. We create the fragment shader. We send the shader to the GPU with data like the color. All right, it can be a color, like we say white or green in our case. And then everything gets colorized in green. And by the way, this one maybe will not be colorized because there is not much in the fragment. So yet again, we can send uniforms like a color. And then this color will be the same for each fragment. We can send a value from the vertex. Did I say that we cannot send? Yeah, we cannot send attributes. All right? Attributes are associated with each vertex. We cannot send attributes here, but we can send what we call varying. And I'm going to use, what color can I use? It can be purple. Yeah, purple is fine. Let me get rid of this one. Let me get rid of this one. We're going to use purple. And from the vertex shader, we can also send data that can be, let me check, where can I write it? I will write it there. So we can send a data that is called varying, like that. And this one comes from there. All right? I know it's getting complex, but the vertex shader will position stuff like that, etc. And the vertex shader, we cannot have attributes inside our fragment, but because right now we are colorizing each fragment, so it's not associated with those vertices. But still, we can send data from the vertex shader to the fragment shader. And if it's going to be for each vertex, and if I think I say it there, yeah, the values are going to be interpolated. By that, I mean that if here you send, I don't know, red, and here you send, so it was green, and here we send blue. When the fragment shader will colorize, I don't know, maybe this one, it will be a mix between green, blue, and red inside that one. And if it's closer to the to this one, so this vertex was green, where those fragments will be mostly green, like that. And the fragments over there are going to be mostly blue, like that. And the fragments over there are going to be red, mostly red. And the further we go, the further we mix with blue and green. The values are interpolated. So we saw attributes for the vertex. It's one value for each vertex. We can send uniforms like the position of the object. So it's, if the position is on the right, well, every vertices will look on the right. We process those in the vertex and we position the vertices here. Then, once it's done with the vertex shader, it's fragment time. We can send again data like the color, so that we are going to colorize everything, or other types of data, but let's keep things simple with the color. We can put the same color on everything. We cannot send attributes to the fragment, but we can send data from the vertex to the varying. But because the vertex are positioning each vertex here, the values get interpolated. When we take care, I don't know, maybe of this one, this little guy here, it's going to be a mix between this one, and this one. And we get like a color being merged. We are talking just about colors, but we can mix anything. I hope you did understand this part. This is the thing it took me months to understand, this structure. So uniforms, attributes, varyings, we have the vertex shader, we have the fragment shaders. Don't hesitate to pause the video, get back to the start and again until you understand. Yeah, summary. So we did say that. Let me check if we covered everything. Yeah, we covered all of this. Yeah, one great question. Why should we write our own shaders? It looks so hard. Why can't we just use 3GS built-in materials that has its own great shaders? Well, there is multiple reasons. First, those materials are limited. And the thing we are going to do at the end of the lesson, it's a very simple exercise, and it's totally impossible to do it with the base built-in 3GS materials, all right? We can just do more. Like, very simple example we are going to, so we have our plane. What if I ask you to just make the plane do something like that? To wave. How can you do that? Well, it's going to be very simple with custom shaders. Also, our shaders can be very simple and performant. The shaders from 3GS are crazy. Like, it's a huge work and can do crazy stuff with light, with a complex algorithm, but it can be bad for performances. They are really well optimized. Trust me on that, they compile only what they need. But if you want to do something very simple, I don't know, like just having a gradient or something like that, and the gradient move, you can maybe do it with the 3GS material, and we do something very complex, bad for performances. Or you can do your own very simple shader, and you will know that it's optimized. One last thing. You are going to be able to do post-processing. You maybe heard this word, post-processing, like in the movies when you change the colors, when you add effect on the screen, when everything is starting to be waving because, I don't know, the player is drunk, like on Sea of Thieves. When you drink, everything starts to get deformed like that. You can do those kind of things. All right, let's create our first shaders with raw shader material. Because we can do two different ways. We can use shader material. So this is a 3GS class that will let us create our own shader. We have shader material and we have raw shader material, and we have to choose one. The shader material will have some code automatically added to the shader code. So it's just some code that we don't have to write. We can gain some time, so it's faster. And the raw shader material is going to be raw, so we have to write everything. Which one are we going to use? Yeah, obviously the raw shader material. I want you to practice and to understand everything. I started with the shader material, and I really didn't understand where those variables came from. I didn't know. Now you're going to understand, because you are going to write everything, and at the end, don't worry, we are going to use the shader material and you will see the difference. So yeah, let's go. Currently, we have a mesh basic material. Let's change this mesh basic material, and we are going to use raw shader material. You save, and you get an error, because we need to provide the shaders, all right? So it's normal if you get an error. How do we provide those programs? All right, these are the programs we have to provide to the material. The material, you provide him a vertex shader, a fragment shader, and it will handle the rest. At the end, after that, we are going to provide more data, but anyway, it's how it's working. You have to provide the vertex shader and the fragment shader in the raw shader material. To do that, you provide an object and you write vertex shader, and you will have to write your program here. Ooh. Don't worry, we are going to fix that. And then the fragment shader, all right? You save. So I provided just two properties, vertex shader and fragment shader in camel case. So we did provide programs, but those are empty. We need to provide a true program inside of it. We can write the program. It will look something like that. All right, with something like that. I will explain everything. Don't do it. And then we provide something like that and something like that, and we have to do everything in one line. Yes, because we are using simple codes. How can we write a program? You cannot do like this. See, you cannot do like line breaks like that. So it's impossible to write a full vertex program here. We're not going to do crazy program at first, but still it's going to be maybe 15 lines of code. So we need a solution. A great solution is called the back quotes. We can also use the terms backticks, acute, and left quotes. All right, there is many names for those. And look at this. They are like that. All right. These are back quotes. See the difference? It's not the same. This is a JavaScript solution. It's called template literals. I put some links on the links panel as always. So we are going to replace those. And the question you might ask is, where is the back quote on my keyboard? And I cannot answer to you. For me, it's over there, but it's because I have a Mac keyboard on a AZERTY, so it's a Mac AZERTY keyboard, and you might have a very different position. I put a link on where to find this button. Sorry, come back, yeah, like this. If you scroll a little, you will have some tips on where to find this back quote, all right? So just find it by using this website. I cannot help you because it's really different between each person, but yeah, you can find it here. We need it because maybe not that much inside that lesson because we are going to use another solution, but in a later lesson, we are going to use the back quotes a lot. So find the back quotes, pause the video if you didn't, and write them here. And then you are going to write the program like that. We're going to write the full program you can see here. It's not that long, but it's the minimum program to get our plane back. We want to see our plane. We provided a plane buffer geometry. With the mesh basic material, we were seeing that plane buffer geometry, but right now with the raw shader, we cannot see everything. I want my plane back. So we are going to write the program here and just write it so that you start to practice and maybe we see that, oh, okay, we have to do this, maybe, and we are going to explain each line inside that program after. But we need a base. So we start with uniform, mat4, projection, matrix, and this. Uniform, mat4, view matrix. So it's a semicolon. Uniform, mat4, you can duplicate and just change the name. Model matrix. What are those? Matrices, like in the movie. Vec3, position, like that. And then void, be careful, don't do any mistake here. It's very important. At the end, we'll be able to test if it's working. If it's not, just check the code and we are going to explain everything. Projection matrix, view matrix, model matrix, vec4, hang on, position 1.0. Each part is very important. I know it's long. I know I'm going fast, but you can pause the video. And so this is our program. So we just wrote this part. All right. Then we have to provide the fragment shader, and the fragment shader will look something like that. It's a little more simple. Precision, medium P. Don't forget the P at the end of medium. Float. Void main. All right, this one seems to be much more easy. GL frag color equal vec4, and we provide 1.0, 0.0, 0.0, 1.0, like that. Did I do a mistake? Yes. So prevision, sorry, it's precision. And yet again, another mistake. I'm not focused at all. No, frag color, let's see. Projection matrix, undeclared identifier, projection matrix. Yeah, I wrote project matrix, it's projection matrix. Bad start. Anyway, it's working. Just write it. So I will just put it there. You can just, so there is a semicolon here, be careful. Pause the video, write it until you get it perfectly and you get your plane back. Then we're going to continue. All right, so this is a way of writing the shaders. We can put them inside those template literals, so those back quotes. But those are very simple shaders. And see, I've done some mistakes, because I was seeing everything is in green, just like in the Matrix movie, and I cannot see if I may have done mistakes. We are missing syntax coloration. And syntax coloration is very important for beginners because you will be able to see maybe something is wrong because it's not the right color. And it will be much like comfy. So what we want is to separate those programs into different files. How can we do that? First, let's create those. So inside your structure, inside the src folder, you're going to create a shaders folder. Because we can have multiple shaders, I know we are going to do only one here, but you can have a shader for, I don't know, the sea doing that, a shader for the sky because there are, like, I don't know, like colors, stuff like that. So you can have different shaders. So we are going to create a folder inside the shaders folder, and I'm going to call it test because it's just a test shader. All right, my structure look like this. I have my test there. So it's src shaders test. Inside the test folder, we'll put those two shaders, and I recommend to call them vertex.glsl. And the other one is going to be fragment.glsl. The name you choose here is not that important, and the extension, you can use different extensions. I know that some people like to use different names. I will show you which one later. Anyway, they will be supported by what we are going to do now. Then you can take the vertex shader content, so this program, and you can put it inside the right file. Be careful not to mix the vertex and the fragment. So I take the vertex shader property content without the backquote, and I just write it there. So I know we don't have syntax coloration, but we will fix that later. Maybe you do have the syntax coloration, but if you don't, I will show you what to do. So I put the vertex shader, you can save it. Don't forget to save it because right now we are going to have multiple files. And then inside the fragment shader, and you can save it too. And as you can see, I also changed the indent so that it's the indent is just right. All right, cool. So first thing, I can hide the sidebar, but you can keep it. If we want to support coloration, if you don't have the syntax coloration, you need a plugin. And we're going to do it for VS Code. For the other, I won't show you, but it's probably the same kind of process, so you will find it. So yeah, to go to the plugin of VS Code, you can go to that icon. And what I recommend is to search for shader. And we have choice between multiple choices. And I recommend to use shader language support for VS Code plugin. Let me check if it's the right one. Shader language support for VS Code. All right, this is the one I've been using for a long time. A lot of people's good recommendations, so I think it's fine. There is probably many other, you can try those, but me, I've been using this one for years, and it's just fine. So you install it. You don't need to reopen VS Code, it seems so. Maybe you need it. It really depends on you and your VS Code. And as you can see, right now we have coloration syntax. All right. And it will be so much easier to write in that environment. I will hide the rest. And be careful, I will use a vertex shader, fragment shader. So right now we have multiple files. We have to switch between them just like I do. So we have our vertex shader inside the file. We have our fragment shader inside the file. Then we want to get rid of those programs and use the file. How can we do that? Oh yeah, for other editor, just pause the video, try to find the perfect plugin and get back to the video. Or you can use VS Code. It's a great editor. Yeah, before we import those files, I need to talk to you about the linter. The idea of a linter is to validate the code and find potential errors. Like just like that, if I do that and I have a linter installed on my VS Code and my computer, the linter will just show an error here and tell me you forgot a comma, which is great, especially for beginners, because this way, without even saving, you know that you did a mistake, which can be really helpful. The problem is that there are some linters, and I put the tutorial from Lewis Lepton. He did a great tutorial on how to install one of those linter. But the problem is that if your code is not complete, like I don't know, you do something like that, you will have an error always showing up because the linter will tell you you are using variables that does not exist. So projection matrix, view matrix, model matrix, which are those. But when we are going to use a shader material, not a raw shader material, we can get rid of those. So you will have an error, but there won't be an error. And I never found how to remove this error. So at the end, I was just not using it. So it's up to you. You can try it if you want. I put the tutorial from Lewis Lepton. Test it and feel free to use it or not. So now we want to import those files. We can try to import them. So let's go on the top, just like we can import images, CSS, dependencies, stuff like that. Let's try to import, I don't know, we are going to call it test vertex shader from, and the path is going to be shaders. All right, it's from my script. So we go into the shaders. I can show it to you there. We start from the script, then we go to shaders, test, and the vertex shader. We start with the vertex shader. So shaders, test, and then vertex.glsr. All right, we can do for both. It's going to be fragment, and this one is going to be fragment. Make sure the path is right. We save. We are not using it now because we have a problem. It looks like we cannot import any type of file. And yes, this is a Webpack problem, a module problem, something like that. It has nothing to do with Three.js. It's just that currently our setup cannot import GLSL. I could have made this Webpack setup be able to import those, but I wanted to show you how to implement this kind of feature to your Webpack project. And other bundler can have similar configuration to do. So I wanted to show you how to do it so you can do it on your own for other projects using Webpack. So we are not supporting GLSL file, and we are going to do that. To do that, you will go to the bundler webpack common.js. So this is where the Webpack configuration is. And we open the common one, all right? It's this one, Webpack common.js. Inside, it's something I wrote. It's just a basic Webpack stuff. We won't explain this because it's a Three.js course, not a Webpack course. But here you have the rules. And the rules are how to handle each type of file. And it will search for, I don't know, CSS, and then use those loaders. We call those loaders. So for the CSS, I said, okay, I want the mini CSS extract plugins to extract the CSS and the CSS loader to apply it, something like that. For the images, I just want to get the files by using the file loader and put them inside the assets images. So when we build the website, they will be inside a different folder. And for the fonts, I did that. I don't know why I used font anyway. I did it. And now we need to add something. So it's inside the rules. Be careful. It's an array. It's at the end. So it's right after the fonts part. And I put a comma here because it's an array. And we can do shaders. It's an object. We need to tell how to test the file. So it's a file that ends with GLSL or VS or FS or vert or frag. All right, this is the way of writing it, and this is called regex. Yet again, it's not a regex lesson. It's not a regex course. I can talk about regex for hours, but anyway, let's just write it this way. So it's slash anti/slash point, and in parentheses, and you can end with $slash. And inside those parentheses, you can write all the type of extensions that are considered as shaders. So we can put GLSL, pipe, VS, pipe, FS, pipe, vert, pipe, frag. So everything that ends with point GLSL or point VS or point FS, vert, and frag, we'll use the following loader. And we can exclude files from the node modules. I don't know if it's really mandatory to put that, but anyway, it's just so that Webpack doesn't use files inside the node modules folder this way. And then we can say use, and we're going to provide the loader we need. So I didn't use the same, oh no, it's the same. Like that, yeah, put a line break, and we are going to use raw loader, which, as you will see very shortly, will just provide a string value. Like it will take those files that end with GLSL and provide you the content just like that. You do whatever you want with that. It's a string. You have your thing inside that string and you do whatever you want with that. So we saved, we refresh. It's not working because we need to relaunch the server. So shut down the server, relaunch it, npm run dev. And did it work? Yes, we don't have an error. So we can hide the console, hide the sidebar, close the webpack command.js file. We don't need to change it anymore. This part will be on every next lesson, so you don't have to write it again. And as you can see, the import seems to have been working fine, and we can log it just like that. And as you can see, I have a string containing exactly what I did before. So this is just a good way to separate your shaders inside different files. It's important to have a nice setup, to be comfy with your code, with your desk, with everything. And you have to spend a little time on it in order to be able to gain time after. So now that we have them inside those variables, so it's test vertex shader and test fragment shader, take them and replace those. So we are still using the previous one, and we can do that, and just replace them. So the vertex shader is going to be the one imported, so the content of this file, and the fragment shader is going to be the one imported, so the content of this file. We save, we get the same result. Great, it's working fine. All right, cool. So now we can code inside of this, which will be much better. And we did that. Yeah, by the way, you can still use some properties we discovered with the materials. Let me give you an example. You don't have to do it, just follow me on that. If I do wireframe, so right now we are using those shaders. By the way, if you want to have fun with the color to make sure that you are using the right thing, the right file, in your fragment shader, maybe change the color. I don't know why we put 0.5 here. We don't know yet what's happening, but anyway, and we get orange. So it's working. We have control over the geometry and the colorization of the fragments of the geometry with our own vertex and fragment shaders. Congratulations, you don't know yet, maybe you don't know yet what you did there, but it's your first shader anyway. So let's get back to the red so we get the same result. And what I wanted to show you is that there are properties, materials properties that still work, like wireframe, true. And we get that. So it's still working, great. And we have multiple of those, like the side. If I remove the wireframe, I can do side 3, double side, like this. As you can see, I can see the front and the back, because just before I could not like this. As you can see, there is no back. So there is some properties that still work. Wireframe, side, transparent, and flat shading. These are the ones I remember, but maybe there are others. Yeah, there are others. But the most important one we saw together. But some properties like map, alpha map, opacity, color, and many other won't work because those are handled inside the vertex and the fragment shaders. And we have to write them again on our own. And it can be really hard. Some are going to be easy, like the color. We are going to learn how to do map and stuff like that. But we have to redo everything inside our vertex and fragment shader. Okay, cool. Yeah, comment or delete the wireframe line. It was just an example. So we wrote this without even understanding those, but maybe you can start to have a glimpse of what's happening here. The shader language is called GLSL. GLSL stands for Open GL Shading Language. All right. It's really close to the C language. So if you've been doing C, you know that it's kind of the same. If you didn't, do not worry, I'm going to explain everything about the syntax. First, you cannot do logs or print, all right? You cannot do console log, don't do it. Just follow me right now. You can practice on at the same time, it's up to you. But I can do like Kiku, something like that. I'll save and I get an error and I cannot see my plane anymore. I cannot do stuff like print, hello GSL. I forgot the semicolon. No, you can't. Why? Well, because these are not handled by the CPU. It's your GPU doing like billions of, not billions, millions of calculations using your programs millions of times at the same moment for the vertices, for the fragments. It makes no sense to be able to log things. All right, so there is no console. If you want to test what's inside this variable, good luck. And I will provide you some tips, but you cannot just log it or print it. The indentation is not important. Like you can do that, you can do that. I save, I get my plan back. Just use the right indentation. Obviously, let's do some clean code. You know, I'm a maniac about that. The semicolon are very important. If I just forget one semicolon, no plane. Which is a problem because I've been writing JavaScript without semicolon, and then we have to switch to semicolon languages. At the end, you just fill it, and when you forget one, you immediately know the mistake you did. So it's up to you. About using a semicolon in the script.js file, I don't use semicolon in JavaScript because we don't need them. But here you need to do it. You have to put a semicolon at the end of each instruction. And you can put many on the same line like that. It will work. As you can see, I get the same result, but this is not clean code. So do clean code. Variables. Let's talk about variables. And we are going to practice. Right now, practice with me. So it's a typed language. If you did never use a typed language, I don't know, maybe you've been using just JavaScript, which is already great. You can do tons of things with JavaScript. In JavaScript, when you want to create a variable, you can use const, I don't know, toto equal tata, rem equal ipsum. I'll put a semicolon just for the lesson. But you do that, and you never said, all right, this is a Boolean, or this is a string, or this is a number, something like that. You don't have to say that. JavaScript will just use the right type by looking at what you did. And you can also change it. Like if I say toto equal a number, then I can say toto equal a string, like that. I can do that. It's a permissive language. We can do those kind of mistakes because actually it's bad for memory management. But anyway, it's better for beginners. So why not? There is pros and cons. In GLSL, you cannot do that. It's a type language. If you want to create, let's start with a float, you will have to do float, foo bar. So you can use camel case, underscore case, stuff like that, or like that. So foo bar equal, and because it's a float, I cannot say, I don't know, like 4. I cannot do that. This is an integer. Yes, there is a difference between float and integer inside of GLSL. But when we are using GLSL, not in JavaScript, I know, but here there is a difference between float and integer. So if you want to write float, you have to do a float with point and something. You have to do it. If I save, it's working. I'm not using it, but it's working. And if I do something like, I don't know, 4, we see that there will be an error because I used an integer inside a float. All right, let's continue. So it was the float. So anyway, you have to provide the type, then the name. So it's not var or const or let. We just provide the type, then the name we want for that variable equal the value, and we have to use the right value. So if it's a Boolean, we have to provide a Boolean. It can be negative values, minus 0.123. It will work, and that's all. Not much to say here. You can do mathematic operations. We will do a lot of mathematic operations. So if I want to do 1, so I cannot write 1, I have to put 1.0, write it. If you're not used to it, it's the perfect opportunity to write it because you need to get used to write a language. And it's all about practicing. A equal 1, B equal 2, and I'm going to do something crazy. A plus B. Wow. Amazing. I did a mistake. I put the equal at the right place, at the wrong place. So it's C equal A plus B. I did a mistake. How could I have done that? Anyway, we can do operation like that. If I save, there is no error. And you can use multiply. You can use minus. You can do divide. And all of these will work just fine. I know we cannot see anything on the screen, but if we did a mistake like this, we get an error. So the next one is the integer. We already talked about the integer. So you can use integer. It will look something like that. Int foo, it equals something, and it has to be an integer, not a float. It's an integer like this. Then bar, it's just random name. And bar, it's going to be -1. Is there an error? No error. Great. We can do mathematical operations like a. Yeah, let's do exactly the same. So it's going to be int a equal 1, int b equal 2, int c equal 4 multiplied by b. All right, but we don't use those a lot because we can get a float by dividing or something like that. So be careful with that. Trust me on that. We don't use integers to do operations usually. What we do is that we convert them. We are going to see that later because we cannot mix. Like if I do float a 1.0, b equal 2, so it's a float with an integer, and then I save, I get an error. And if I try float, I get an error too. All right, I cannot mix them. But what I can do is to convert those. So I start with, it's going to be a float a equals something, so this one is right. Int b equal to, this one is right. And then we are trying to mix them, and we cannot mix them that way, but we can convert them on the fly by doing, oh, all right, my b is an integer, but now I want it to be a float, and I can do just like that. And now it's going to be a float. Be careful. I say that c is a float. If you put int, while you multiply a float with another float, you cannot get an integer. So you have to provide a float here. The next one is Boolean. Yes, we can do Boolean, and it's just true or false. Like float foo equal true, and if I did a mistake, bool foo equal true, and bool bar equal false, like that. We save, no error, great. We don't use much Boolean too. And then there are some really cool ones, and they are going to be really useful, and it's the hard part. All right, we just saw float, int, bool, and now we're going to talk about vec2. And those are the vector2. I'm going to show you one and you will understand, I think. It's going to be vec2 foo equal, and to create a vector2, and you know about vector2, it's the same as the 3GS vector2. We do vec2, all right, it's short version, don't forget the semicolon, and you have to provide two values because it's x and y, and it works just like that, just like 3GS, so 1.0, 2.0. So it's 2D coordinates containing x equal 1.0 and y equal 2.0, and I can use like negative values just like that, and it's working. Great, it's just 2D coordinates. We'll be able to calculate things with 2D coordinate, but there is a lot to say about those. If you are trying to create an empty vector2, you will get an error. All right, it's not like in 3GS where you can just create a vector2 and the values will be 0. Right here, you cannot do that. But you can provide only one value, and this value will be used for both x and y. You can also change the values after, so because it's x and y, we can access those properties just like in JavaScript by using the variable x and do something equals something else. All right, we can use them, but we can also change them. So I said that now at the beginning it was 0, 0, now it's 1 and 2. As you can see, no error. Doing operation on a vector2 will multiply both the x and the y. So if we have something like 1.0 and 2.0, then we can multiply it, and I can multiply it like this. So multiply equal 2.0. Be careful, I always put semicolon and 0 because it's a float. I will get 2 here and 4 here, because when you multiply by one float, all the values, all the properties get multiplied, which is actually a great feature. We will use it quite a lot. Then we have the vector3. Good news, it's just like a vector2 with just one or two more cool features. So if you want to create one just for the sake of the lesson, we are going to do vec3 equal vec3. And we can provide one value, and as you can see, it's working. You can also do vec3 bar equal vec3 3. So it's just what we learned from the vec2, but applied to vec3. 1, 2, 3.0 like that. Still working. And we can do bar.z equal, dot bar z equals something else because it's x, y, and z, and we get something that seems to be working. Great. Instead of using x, y, and z, we can use r, g, and b. And we do, let's say, a color, because color are RGB. So we can create a vec3, let's say a purple color, like this, and do vec3. So we start with something, so 0.0 like that. And then we change its value, and to get something purple, I'm not sure of that, but still, let's use it. Oh yeah, that's it. So it's the red is going to be lower, so it's 0.5, something like that. And we have to add more blue, so we are going to do blue equal 1.0. These are just arbitrary values, all right? It really depends on how you want to use them, but we usually consider the R, G, and B values to go from 0 to 1. So if it's 1, 0, 0, well, it's like the red is strong, so you're going to get a red color. But you can do whatever you want with those values. And we can mix them, like I can do I did R and B, I can do X and B. And this will work too. It's just aliases, all right? You can use X or R, Y or G, and Z or B. It's just aliases. We just use RGB when we are talking about colors. Yeah, we can create a vector 3 starting with a vector 2. So you create a vector 2. Let's say a vector foo equal, and we put a value inside of it. We put 1.0, 2.0. So we start with a vector 2, and we're going to create a vector 3. It's going to be bar equal vec3, and the first x and y value are going to be fetched from the foo. So it's the foo x, foo y, and we just provide foo. And then we provide a third value. It's going to be the z right here. So it's going to be 1, 2, 3. We could have write something like x and foo y. It's the same result, but we can do this kind of things, all right? This will result in 1, 2, 3 inside that vector 3. You don't have to do it. And there is an even better way. If you create, let's say, a base value, which is a vector 3, we call it foo again, and we use, I don't know, vector 3, and we do 1.0, 2.0, 3.0, and we want to create a vector 2 that is based on, I don't know, maybe just those two values here. We can create a new one. It's going to be vec2. We call it bar, and we do foo x, y, just like that. As you can see, there is no error. I created a vector 2 by using the first two values of the foo. And one really cool thing is that I can write anything here. I can write x, z. So I will get a vector 2 composed of 1 and 3. So the x will be 1, and the y will be the z, so the 3. And I can even like invert them. I can do y, x. So it's going to be x equal 2 and y equal 1. All right, this is called swizzle, and we can use swizzle a lot. I don't use it because I know that if some people get in my code, they will just ask, what's happening here? Is that even possible? So I try to keep my code simple, but you can use swizzle just like that. I mean, inverting like that, I really never do it, but you can do like a small vector based from a bigger vector like that. Yeah, the swizzle order can be different. And finally, there is a vector 4. It's like the vector 2, it's like the vector 3. There is nothing to say about it, but that there is a fourth value, a fourth property. So let's create one just for the sake of the lesson and to practice. So vec4, I put one value, a second value, a third value, and a fourth value, like that. And then I can just, I don't know, like create a float bar equal foo x, or foo y, or foo z, or foo, what's after z? Well, there is nothing after z, so they decided it's going to be w, all right? Too bad there is nothing after z. They didn't plan that when doing x, y, and z. But anyway, you have to provide, you can access to the fourth value by using w. And if you are using RGB, well, there is also an alternative, an alias, sorry, it's the A, right? A and W is the same thing, it's 4 right now. While why A? Well, because A for alpha. So you can get a color with alpha. It's just a syntax sugar. Like you can just write things that makes more sense by using RGBA instead of X, Y, Z, W. All right, that's cool. And you can do tweezers, stuff like that. And there are other types like mat2 for matrices 2, mat3, mat4, sampler 2D, stuff like that. But we are not going to discover them here because we cannot test anything yet. All right, we are just learning how to write things in GISL. We're going to use more complex stuff later once we have more control and we know what we are doing. Next thing is about function. We can create function. I won't spend too much time on it because we won't use, I don't think we will use functions in the next lesson. You can create a lorem ipsum function. This function will do stuff like a equal 1 point something, b equal 2 point something. And this will return the result of 1 and plus 2. So it's going to be a plus b. As you can see, we use, it's pretty classic, like we have a return, we have a function that looks like this, and we can call this function and do, I don't know, a float result equal and call this function. I know I'm going fast on this one, but it's because there is no surprise. It's like almost any type of functions in any language. The new thing is that you have to provide the type here. All right, if your function is returning a float, because right now we are calling this function to get the result, which is a float, you have to say that it's a float. All right. And obviously you can add parameters. Oh yeah, if your function is just here to do things and not return anything, like, I don't know, it does something like that, you can say void. All right. And we already have a function void. It's the main function void. We're going to talk about this one. It's the void function main. Sorry. And you can also provide parameters. So if I get back to this, so it's a float. Sorry, I'm going too fast, but it's not that important. So we can say float a, so it's the first parameter, comma float b, it's the second parameter, and you provide the result. So you return a plus b. Don't forget the semicolon, like this. And we get an error. Let me check why. Lorem ipsum, float result lorem ipsum, we call it, oh, I forgot to add the parameters obviously, so you have to provide 1.0 and 2.0 or anything, and it will add 1.0 to 2.0 and return the value. Yeah, this function has no sense, but it was, it's meaningless, but it was just for the purpose of the lesson. You also have access to many built-in classic functions, just like in JavaScript when we are doing sinus, cosinus, stuff like that. So you have sinus, cosinus, max, min, po, x, mod, clamp. So maybe you know this one, modulo, sinus, power, stuff like that. But you also have access to more complex functions, which are great because it's really useful, like cross, dot, mix, step, smooth step, length, or you know this one, distance, kind of the same thing, reflect, make a vector reflect, refract to make a vector refract, and normalize, I think you know about normalize, we talk about this one, is so that the vector get a length of 1. We are not going to use them because we still don't have any changes here. Well, I just want you to know that those methods, those functions exist. And we're going to talk about documentation right now. The problem is that there is no beginner-friendly documentation. Usually I just do a search on the web and I end up on those 3 websites. There are other things, maybe you can end up on Stack Overflow, stuff like that, but those are pretty good. Like we can get a lot of information here. I don't know, maybe you want to use the cosinus, you don't know what to send to the cosinus, or any other value, like how to use the dot, the cross, stuff like that, the clamp. You just do a search on the web and you mostly finish on those websites. So we have Shaderific. I put the link as always, the links as always in the links panel. So this one is great because it's one page and you can get a lot of information. Just search for, I don't know, clamp, and you will see how to use the clamp and have a cool description. You also have the Chronos group. Yeah, we talk about the Chronos group. And as you can see, this one is huge and it's because it's for OpenGL, not WebGL, but still we get access to common function like clamp. As you can see, there is a documentation for the clamp and a lot of examples. This one is pretty useful. And the next one I sometimes end up in is the Book of Shader. We're going to talk about the Book of Shader later. And there is a glossary with quite a lot of function in here. Have a look to the book of shader. I will talk about it later, but still, sometimes I end up in this one, and maybe I can just check the dot, and you will also have examples, and you can tweak those examples, so it's really cool. Like, I don't know, I can put 4, and as you can see, it's changed something there. So yeah, this website is really awesome. We're going to talk about it later. So next part. We know how to use the GLSL language, so we know that we have to do types, variables, we know how to use vector2, vector3, we can create function. Let's get rid of it, by the way. We don't need it here. And we know that we can multiply stuff, etc. So now we can try to understand what's in here. And we have a lot to say. First, we talk about the void main function. This function will be called automatically, all right? You need to have this one on your code, and let's say the GPU will call this function, and everything in it will happen, all right? It's automatic. You don't have to do main like that. No, you just put it inside your code and it will be called. It doesn't return anything, which is why we get a void. I know there is something happening here, but there is no return something, all right? Which is why we have a void. Inside of it, all we have is our GL position variable. This is a very important variable. It already exists, like we didn't have to do like something like GL position equal vec4, something like that. But anyway, we are reassigning it, meaning that we are putting something inside of it. It will contain the position of the vertex on the screen. All right, this is the part where at the end you do this huge formula, and at the end it will position the vertex at the right place on the screen. I should have said on the render, all right, on the render coordinates. We need to learn a few more things about that. This long instruction will return a vec4. That's strange because we said that this is like the render, and the render is in 2D, but still we have to provide a vec4. And I will explain to you later why. So if those is a vector 4 and position the vertices on the render, can we do something like that? Like GL position x plus equal 0.5. Can I do that? Let's save. Yes, it did work. And I can play with the y. And yes, it did work again. It went up. So yeah, we can move things like that. It's the wrong way of moving things, but we can do that. Don't change this like that, because there are things happening. I will show you how to really start to make things wave and move right after. So yeah, the question is why 4 values? And I have to warn you right now, I'm not an expert about that either, but still I will tell you what I understood. It's because the coordinates we are providing are in fact in clip space, and a clip space will not look like this. It's not a 2D coordinate. It will look more like a box. Imagine like that. It's like a box where your camera is somewhere, let's say over there. It's looking at the scene. I'm going to use I don't know, white. So my camera will look something like that. Let's try to do something like looks like a camera. And this is my clip space. And when I position thing inside that clip space, let me add just those one. So it will look something like that, and something like that. When I position the vertices on my render, in fact, I'm positioning in that clip space, and it will be, I don't know, something like that. You cannot feel the depth, but trust me, there is depth. Why we need that? Well, because the third value, so there will be the x, like that. So it starts from the center, but let's say it's the x like that. So I wanted this one. This is the x. We will provide the y, but we also have to provide, let me put y. We also have to provide the z, like that. In fact, they start from the center, but anyway, we provide the z so that we can know which geometry vertices are in front of the other. We need to know the depth, which is why it's in fact positioned in this box. It's just like a spherical box. It's not like a real box in 3GS, but this is why we need a third value. And the fourth value, I never understood about this one. It's about perspective. All right. I don't know what's happening here. It's about, there is a word about this. I forgot, but it's just about perspective. If you want to know more, I provide you some articles. I think it's going to be later. Anyway, check the links in the links panel. So yeah, we have to provide this, but still we can play with the X and the Y so that the object goes up and on the X, also horizontally and vertically. And I never had to play with the Z and the W. Never. Next part is about the position attribute, because as you can see in my code, there is a position part. And we know about attributes. Remember, the attributes is the data that change between each vertex, and we can get it inside the vertex shader, which is exactly what we are doing right now. With this code, we are just retrieving this value from the geometry. And remember what we did with the geometry? We created a buffer geometry, and then we provided an attribute by doing, you know, the float 32 array, stuff like that, buffer attribute, where this is those values. This is the value we provided in the JavaScript when we were creating our own buffer geometries. And those values are provided by Three.js when we create a plain buffer geometries. There is a position attribute. The name of the attribute is position, and we can get the values of each vertex by doing that. And it contains the X, Y, and Z coordinates from that attribute because it's a vec3. All right, cool. So the program, we have a different value here when you're using when positioning this one, this one, this one, and this one. But still, if you remember, we have to provide a vector 4, and we are going to convert the position to the vector 4 by adding. So we are using the X, Y, and Z of the position, and we are creating a vector 4 based on it, and we also add a W equal to 1.0. All right, we are just converting the position to a vector 4 because those matrices are mat4. We're going to see that later. And at the end, we need the clip space position. So it's the position inside of that. All right, cool. Actually, I'm explaining, I try to explain everything, but you will see that you can manage without understanding everything. But still, it's great if you do understand everything. And finally, all we have left is this part and this part. Those matrices. Do not worry, it's not going to be that hard. Each matrix will transform the position, so this one. So we have a base position, it's just a coordinate of that plane. And each matrix here will transform this position in order to, at the end, position the vertex inside that clip space. So inside our render, we will apply different matrices until we get the clip space coordinates. There is currently 3 matrices. Those are uniform because it's the same matrix for every vertices of the geometry. Yeah, in each one we do a part of the transformation, and to apply a matrix to a vector, this time it's a vector 4 because it's matrix 4. Yeah, so by the way, you have to use matrix 4 on vector 4. You can have matrix 3, mat 3, and you can use them in a vec 3. And to apply a matrix on a position, so I don't know, we have a coordinate, we want to apply a matrix, you just multiply it, and this matrix will apply it, so the vertex, the coordinates get somewhere else. And we have 3 of them, and we are going to explain those. The first one is called model matrix. I could have put it up, but anyway, the order of the uniform is not important, so you can just import them in different order. And the first one is the model matrix, and it will apply transformations to every vertices relative to the mesh, position, rotation, and scale. All right, if you do, I don't know, let's get back to the script, just follow me on that. If I do a mesh position x equal 1, just like that, I put a semicolon, my plane is now on the right because the position, transformation, and rotation and scale got converted to a model matrix, and we apply this model matrix to the position coordinates. All right, it's just like that. You don't have to write those matrices. You just provide a position, a rotation, a scale, and 3GS will do the heavy lifting and convert those coordinates to matrices. All right. Yeah, it's getting hard. The next one is the view matrices, and this is about the camera, because as I said earlier, it's the same problem. If my camera is further away, well, the vertices should be shrink like this. If my camera look on the left, well, the vertices should go to the right of the clip space. And if my camera field of view is small, well, the object should look bigger inside the clip space, all right? Because it's like I'm zooming, where in fact, at the end, the vertices are just expanded inside the clip space. So this is the view. So it's camera matrix, but we say view matrix. And finally, there is the projection matrix, and the projection matrix will transform the coordinates into the final clip space coordinates. All right. It's like the matrices are moving because of the object transformation with model matrix, and then they are moving because the camera is somewhere else looking on the side, something like that. And at the end, we need the clip space coordinates, so the one inside that little box, and we use the projection matrix, this one. And we have to do it in that order. So we start from the position attribute, we apply the model matrix, we apply the view matrix, and at the end we apply the projection matrix. Great. I put an article, yet again, if you want to know more about this is a great article. It helped me a lot to understand those. Check the links panel. We also have a shorter version, and you might see that in other shaders, 3GS shaders. Oh, by the way, those are provided by 3GS. I told you that the 3GS will convert the position, the scale, the rotation to matrices, but this is very specific to 3GS, all right? And we have a shorter version where we can use, don't do it, just watch me on that. Instead of having a different matrix for the view and the model, you can just have one, and it's going to be model view, and it's a mix between those two. And instead of multiplying the view matrix with the model matrix with the position, don't do it, because we are going to remove it. You can just do that. All right, you gain few characters, why not? And it's working great. It doesn't change a lot about performances, but you can do that. So let's get back to what we had right before, and we are going to do even worse. We are going to separate each part, so we can understand more, and it will give us more control. So I will comment this one, and I will start with the model position. So I will do vec4, because I'm going to create a vec4. I'm going to call it, so I can choose the name. It's going to be the model position. So I have the base position. Now I want the base position being changed, transformed by the model matrix. I will do model matrix multiply by, we need a vec4, and it's going to be position 1.0. All right, I converted the position attribute to a model position by using the model matrix. I can continue. Vec4, I need the view position, and I'm going to use the view matrix to modify the model position like that. And I don't need to specify vec4 because it's already a vec4. And then I can do the projected position, so projected position. Now we do projection matrix in order to get my clip space position, and do view position. And this is exactly what we did here, but with more steps and more variables, because at the end I can just do that. And we get the same result. But now we can play with the model position and do something like that. Equal plus 1, and as you can see, my plane moved up because I can play directly on the position here. And we can have more control, because right now, instead of just moving the whole thing, what we can do is do some things like that. Just look at this. We are going to make, so I remove the Y, as you can see, it's like that, and we are going to make our plane move like a flag, like this. So it's going to be on the Z, and you can test, because the Z is the one coming toward us by default, because my camera is positioned like that. Just to test if I'm right, what you can do is just increase it, do something like z plus equal 1.0. And as you can see, it was too close. So I'm going to do 0.5. And yeah, you see it's moved forward the camera, so it seems to be working. And right now we are not going to just move all the vertices. We are going to move the vertices, but according to the x. So I'm going to use, look at this, I'm going to make a wave value. Remember the scene? So it does something like that. And in the angle here, I'm going to use the model position x. Look at this. Yeah, we get something. So it's like it's moving, but I cannot see the waves. It's because the frequency is not that high. You need to multiply this one to get a better frequency, a higher frequency. Okay, it's look like this, and you can see that it's working. But the problem is that it's going way too far because it goes from -0 to +0 because we are using a scene. Then we can just multiply it by a smaller value like 0.1, or you can divide by 10 and you get this. It's working. Good luck getting this result without using a custom shader. With just one line of code, so we did separate model position, view projection, projected position, sorry, but this one can be put inside of this one. With just that line of code, we start to get things moving and we have control. Like if I do, I don't know, 20, I have more waves. And obviously you can guess that we are going to animate this and add it to that UI and stuff like that. So this was the vertex shader. I hope you did understand. The most important part is that now we can control the position from the model position right here. If you don't understood the clip space thing, this matrix about view and projection matrix, it's okay. You can just use this code. This is the important part. Now we're going to talk about the fragment. We will get back to the vertex shader soon, but now we can understand the fragment. Good news, it's going to be easier. Inside our fragment, the first thing we have, no, it's not the first thing, but still we have our void main, and it's just like this. So this is the function that returns nothing, so it's void, and inside of it we will do some instructions, and there is only one instruction. Then we have the precision. Let's talk a little about the precision. We need to decide on the precision of a float, like how precise can be a float. Is it something like this is the maximum precision, or is it something like that, or something like that? You might think that it's not that important, but it can be. I don't know if you have like huge values or very small values, or you can zoom out a lot and then zoom into a very small object on your scene. Well, this can have influences on your the render. Here we are going to use the default one, which is medium P, and we have to provide it. You might get an error if you don't. High P can have performance hit and might not work on some devices. So having a huge precision, it's more than just having a float precision, but let's think about it that way. This can have performance hit and might not work on every devices. Low P, so we can write low P, can create bugs by the lack of precision. Like you move a very small object, it doesn't move, and paf, suddenly just move a whole block because it's not precise enough. And usually we just use medium P that should work on every devices, and you will have enough precision. When we are going to use the shader material, this will be handled automatically by 3GS, and it will be much simpler. I don't know much about precision. I just know that when I had like a low P, I had this bug of things moving too much, and a high P just didn't work on some devices. Then it's the final part. We have the GL frag color. Look at it, try to guess. I think you can understand what's happening here. It's like the GL position that was positioning things inside the clip space, but now we are just putting a color on each fragment. So remember that the fragment shader will color each visible pixel, so fragment of the geometry. So those one in the middle. And as you can see, it's 1, 0, 0. So it's RGB. So it's a full red, no green, no blue. And the last one, you can guess what it is. It's the alpha. Yes, it is. And no surprise. So if we try to lower the alpha. Let's put something like 0.5, and it's not working. And I forgot something from a long time ago. We have to activate the transparency. So we have to do transparent true, like that. And the alpha is working. If I had something behind, I could have seen this thing behind. All right. Right now we just have this, so it just looked like a darker red, but anyway, it would have worked. Activating the transparency is doing actually a lot more than what we can think, but still for us it's just working this way. So yeah, let's get back to the vertex and play with attributes. By default, there is this position attribute, and actually we can see those if you go to the geometries, you log this geometry. So it's a buffer geometry, so it's a plain buffer geometry, so the base is buffer geometry, and we can check its attributes by going into the attributes here. And as you can see, there is position, normal, and UV, and we start to know about those. All right. The position are going to be the position of the vertices. As you can see, there is a lot of them because there is a lot of subdivisions. The normal is the outside of the vertices so that we can, I don't know, do light stuff. And the UV, it's the how to place a texture on this one. Let's remember those. It's always useful to know about those. We use them a lot. We can add our own attributes and get them inside the vertex shader. So by default, there is those 3 attributes sent to the vertex shader, and we did get one here. We could have get the other ones. We will use one of them later, but we did get the position one, and right now we are going to add our own attributes. And we say at the beginning of this course that we are going to do that. What we are going to do now is just provide random values and move the vertices randomly. Like we are going to have spikes everywhere on our flag. I think we remove the waving stuff just to focus on those spikes. So it's just a test. It's for the sake of the lesson. So we want to add random values and get them inside the vertex so that I can move the vertices on the Z according to this random value I've created inside the script.js file. So let's go first. I need to know how much I need to add. So I will do count equal, and to know how much, well, I need to know how much vertices there is inside my geometry. And I can get that by doing geometry, attributes, and based on the position count. All right. I know that positions are vec3, so we have 3 times more, but this exact count, it's not the length of the array, it's the exact count of vertices. All right. So we can just use this one. Then I'm going to create a float 32 array. You know about this one, I hope. So const randoms equal new float 32 array. And I will use the count. So it's the length of the array. And then I need to fill it with random value. I will do for let I equal 0, I inferior to count, I plus plus. And I just want to fill that array, that randoms array, with random value. I will do math random. All right, looking great. You can test it if you want. It's going to be huge, but anyway. Oh, I did a mistake. Const variables, const random. Oh, sorry, I have to fill it, so it's going to be random. Y equal math random. Yeah, like that. Refresh, and yeah, this is the array filled with random values. So if I get those, you can see that it's just a bunch of random values. Then I have to provide it to the attributes of our geometry. And we can do geometry, set attribute, a random, and it's new 3 buffer attribute like that. And we have to provide this float 32 array and say how much values to take from that array for one vertex. For the position, well, we need 3. It's X, Y, and Z. But right now, it's just one random value per vertex, so it's just 1. We save, finger crossed, no error. Great, we can continue. So we added 1, and if you want to check, you can, like log the geometry. We get our same geometry, and if we check the attributes, we get the A random. And I did use A because A for attributes. I know that 3GS doesn't do that, like it's normal position UV, but I really like to do that, and it will get handy right now. I mean, in few minutes. So if it's attribute, I use A. If it's a uniform, I use U, and if it's a varying, remember the varying, it's the one we send from the vertex to the fragment that gets interpolated, I will use V. You don't have to do it, but it's really useful. It did help me a lot to get a clean code. Alright, we can remove the console log, get back to the vertex shader, and to retrieve this attribute value, which will be different for each vertex, we can do attribute, and it's going to be a float. So it's not a vector 3, it's a float because we only have one value per vertex. So float, because we said 1 here. And we are going to use a random. So this is the name we chose here. If we put anything else here, we have to put the same thing here. We just save, no error. This is great. Sounds, looks like it's working. So instead of playing with the model Z like that, I'm going to do model, so same transformation, model position Z, so it goes to the camera, plus equal, I will use this random value, and we can test just like that, and as you can see, it's working, but it's way too strong. So what we can do is just lower it down a little by multiplying by 0.1, and yeah, it's working. And we can have like a terrain, or I don't know, like it's a trap where the player will be crushed by spikes or stuff like that. That's cool. That's really cool. We are going to go a little further, and we are going to color the fragments. So right now it's just all red. It doesn't look cool. Like if we are right in front of it, we cannot see the spikes. What we are going to do is get this value to color the fragments. So if the random value is close to 1, we will get one color, and if it's close to 0, we get a random color. This way we are going to be able to see the spikes. For that, we want to send data from the vertex to the fragment. As we said multiple times, we are going to use varying. I repeat, we cannot use attributes inside the fragment. I cannot do something like that. I cannot do that. I cannot get attributes, but I can send data from the vertex to the fragment. So here we go. We are going to use a varying. I like to put the varying after, so it's uniform attribute varying, and I will do varying, so it's singular. You have to choose the type because it's a variable. It's going to be float, and I'm going to call it v random. And this is why I always recommend to use va and u, so varying attribute and uniform, because if you have the same name and you call it random, well, there you call it random and you will have a conflict because it's going to be the same name, and you cannot have the same name for two variables. It's logical. So this one is a random, it's the attribute. This one is vrandom, so I just created it in order to then change it. I can change it anywhere in the code. The important thing is just to change it. I can do it after. I will do vrandom equal a random. So I take the attribute value and I put it inside the vrandom. I save, no error, but we get a warning. A warning telling us that we have a vrandom declared in the vertex, but we are not using it in the fragment. Thank you WebGL, thank you 3GS. It's great to be aware of that because it can take resources and it's bad for performances. So we are sending a varying, but we are not using it here. And by the way, we are going to add a varying like that. All right, so let's do that. Inside the fragment, to get the varying, we just have to write the exact same thing here. It's like creating it, but in fact, it will contain the ones coming from the vertex. All right, right now I'm inside the fragment, and then we can just use it because it's just the value, and I will be able to use it. Let's use the same value as me. I think it's some kind of purple bluish thing, and there is an error. Sorry, let me check that. Poof, editing, and then I'm going to use the v random value like that. And it's looking great. Actually, I want a purple thing. I have to change this one too. Yeah, this one is looking great. It's just random value. See, I just play with the fourth value, which is RGB. So it's the B. I added more blue and I get a different result. If you want, I don't know, maybe more something like that. Yeah, why not? Maybe something like that. So both are going to be like this. This one is going to be like that. You can just play with those and get different results, and it's looking great. Look at that. And as you can see, when coloring this part, this pixel where I'm pointing right now, so there is one varying here and one varying here, And when the fragments get colored between those, they will be interpolated, all right? There is a result here, so a V random here, a V random here, and between those, there will be a different value. Like this one is 0, this one is 1. Between them, we are going to get 0.5, all right? It's the interpolation thing happening here. The varyings are interpolated. Great. Let's get rid of that. So this was a great exercise. I really like the way it looks. Have fun. Yet again, send me what you are doing. I want to see what you are doing. I will be glad to see them and even share them on the web if you want. So yeah, I'm going to get rid of this to get back to the initial result. And the varying part. Okay, let's get rid of the varying too. You can just comment them. I will remove them, but do whatever you want. And I'm going to get back to the red plane, I think. So 0.0, 0.0. All right, follow me on this. Oh, I did a mistake. Let me check. Oh yeah, I have to remove the vrandom thing here. Back to the plane. We're going to talk about uniforms. We will do cool stuff again, don't worry. You just have to restart from a good base. So make sure you have everything the same way. So this is the vertex, pause the video if you have an error, and this is the fragment. All right, I remove the varyings and get back to the red. So the uniforms, we talk about the uniforms, it's the value that are the same for every vertices or every fragment. We can have a color, we can have a position, we can have matrices and stuff like that. It's useful if you want to have the same shader, but with different results. Just like you can have a mesh standard material and you can create, I don't know, 2 spheres and one will be red and one will be blue. It's exactly the same here. We can use the same material using the same vertex and fragment shaders, but send different parameters so that one is blue, one is red, one is up, one is down, one is shrink, one is like, I don't know, animating faster than the other. The second reason is being able to tweak the values because we are going to be able to change this uniform on the go. Like we can send an animation value, we can send a color that changes or stuff like that, and you will be able to see this value change on the render. And yeah, so yeah, it's the point here. We can animate those uniforms, and we will do that together today in this lesson. The uniform can be used in both the vertex and the fragment shader. So this is great. We can just use the same uniforms in both the vertex and the fragment. Let's add one. I will get back to the frequency thing. Oh, I should not have removed it, so I will help you get it back. So put this back here, here, and here. All right, it's looking like that. All right, so this is our flag. I just added this part. You don't need this part. Let me check. Yeah, like that. Just put back this little flag thing so we get waves, and we are going to be able to control the frequency from a uniform. Like I want to be able here in JavaScript to control this value. So instead of 10, I will be able to put something like 20. I get something else, another result, I mean. To do that, it's pretty simple actually, so great news. We don't need the transparent, so let's get rid of the transparent. It's going to be uniforms. And to provide a uniform, you have to choose a name. And as you can see, I'm going to use U frequency. Yes, I put a U because it's a uniform so that it doesn't conflict with attributes or varying of stuff like that. And to provide the value, you cannot just put 10. You have to provide an object that looks like this. All right. Then. Oh yeah, by the way, maybe you're going to explore the web, see some codes, and you will see something that looks like that. All right? Or maybe something like that, or that, or that. This is the old way of doing it in Three.js. All right? You don't need to provide a type anymore. You can just put the value right here, but still it has to be inside an object. If you see type something, you don't need it. You can get the code that you need, remove the type part, but still you need an object like that. So no error, let's continue. How do we get this frequency? It's that simple as that everything we already have here. Just like we got the projection matrix, view matrix, and model matrix, we didn't have to provide those because Three.js handled this nicely. But now we need a new one, so it's going to be uniform float because it's just a float value. It's just a number in JavaScript, so it's going to be a float here. And we can do U frequency like that. And we just got this value here. Pretty easy. Sometimes it's not that hard. And then we can use it right here. And as you can see, we get the same result. But right now, we can change it from the JavaScript. And we can change it on the fly, like we can animate it, we can put it inside our .UI and stuff like that. So this is great, but we want to be able to control the like the waves on the X, which is the case here. So it's moving on the Z, but we see waves on the X because we are using the model X. And I want to be able to control the waves on the Y too. So let's do that. Instead of sending one float, it's just one frequency, we're going to provide a vector 2. So 3, vector 2, like that. And I'm going to provide two values, 10 and 5. So it's going to be the same one on the X. It's not working because I'm sending a vector 2, but not getting a vector 2. So I will send 10 on the X, so we get the same shape, but also on the Y, but it's going to be a different frequency. Then to get it inside our vertex shader, we replace the float by a vec 2. All right, it was a 3GS vector 2. In a GSL, a vector 2 is written like this, vec2. It's a type vec2. And then we can use it. So we are going to move it on the Z in both X and Y. So on the model X, it's going to be frequency X. Let's just test this one. So we got back our X, and now we are going to move it again on its D, so toward the camera, but we are going to use the Y position to make the scene value change. And we're going to use the Y frequency here. And as you can see, we get different results that are looking great. So as you can see, the frequency is higher, so it's a more amplitude on the Y than on the X, as you can see here. We have more here. And we can control it. As I said, we are going to add it to the .GUI panel. So right after creating it, there is no surprise here. You can do GUI add. You have to provide the concern object. So it's going to be material, uniforms, U frequency. So this is the way of getting the uniform here. So it's material, uniforms, U frequency. Be careful, we are not changing the frequency. It's a common mistake. I do it again even today. I just try to change the frequency. It's not the frequency, it's the frequency value. So value. And because it's a vector 2, the properties we want to change are the X, and we will do the Y later. So we are changing this vector 2. By doing that, it has nothing to do with the shaders. We are just changing the X property of this vector 2. And we can set a mean value, so 0, a max value, I don't know, 20, should be enough, a step to 0.01, and we can call it like frequency, we can call it, what did I use? Yeah, frequency X, something like that. Sorry, it's really long. I will zoom out just for now, so we get something like that. This one is going to be Y, and the name is going to be frequency Y. And then I zoom in again, and we get this. So we can control the frequency and also on the Y, and you have full control over those like that. Now that we have our frequency being able to tweak them, we are going to animate things, just like it was a flag and the wind were passing through the flag and the flag were doing something like that. All right, how can we do that? Well, there is many ways of doing it, and we are going to use a time value that we will send to the vertex shader and then animate our vertex shader using this time value. So first, what you can do is add a new uniform. All right, it has nothing to do with the frequency uniform. It's just a new one, and we're going to call this one uTime. As always, I start with U for uniforms. Often you will see different things from different developers, but I recommend you to always put the U. And the value is going to be 0, and we are going to increment this value in the tick function. So you can just save, make sure that everything is working, no error. Now what we want, instead of updating the uniform by using this .UI, we're going to update the uniform in the tick function. So let's go. We already have the time. It's in the elapsed time. I can show you the result. It's how many seconds passed since we reloaded. So it's been 3 seconds, 4 seconds. All right, we can use that value. So let's go. You can put it anywhere you want. I'm going to put it there. I'm going to do update material, sorry. To update it, it's just like we updated the frequency. We have to do material, uniforms with an S. The name of the uniform is uTime. And we have to change its value, not the uTime directly. It's the value of uTime. And it's just a float, remember? It's not a vector2 or something like that. It's just a float. So we just need to change the value. So it's going to be elapsed time. We just send the time to this uniform. We save, no error. Great. Then we can update in our vertex shader. First, we need to get this uTime, and I will do something like that. See the mistake? Yeah, I use vector2. It's not vector2. It's one value. It's a float. So we do something like that. Yet again, just save. If you did a mistake, maybe you forgot a semicolon, something like that, you get an error. So fix the mistake and then continue. What you can do now is use this time value. But first, I want to show you that this time value is working. What you can do is model position Y. I just want to make sure that the time value is working. I can do plus equal uTime. And look at this. It's going to be quite fast. All right, it seems to be working. It's going up. I'm not touching anything. Let's refresh, and it's going up. So it's working. Our uTime is being incremented, but because we are updating it in the tick function right here. So instead of doing that, what we are going to do is offset the value inside the scene so that our scene is doing something like that. All right, and because we are using the X and the Y, well, we have different waves depending on the X and the Y. And what we are going to do now is add the uTime. So we can do uTime. So plus uTime like this. And that's all. And we get a beautiful animated flag. I'm just going to invert it. I'm going to do minus uTime like this, so that it goes in the other direction. It always feels better when it goes to the right. All right, that's cool. And that's all. You can provide other values, all right? I did provide the uTime. This way I can use the uTime for many different animation. I don't know, maybe the flag is then like rotating like that or something like this. We are just going to use it for the waves animation. But I really like to send just the time and use it however I want inside the vertex shader. All right, it's looking great. One thing people do is use the date now. Maybe you remember from this one. I can show it to you. It's date now. Look at the logs here. And we get this value. This is a timestamp. It's how much millisecond has been spent since the 1st January 1970, something like that. It has something to do with Unix, history, stuff like that. Anyway, yes, we could have used this, but it would not have worked. Because the value right here, it's too big. We cannot send such a huge value to the uniforms. So be careful. You cannot use huge values like a date now inside the uniforms. This is why we use the elapsed time. Remember the elapsed time, it's not millisecond, it's second, and it's from the refresh moment. So it's just 4, 5, 6, so it's okay. Be careful with too huge number. I lost so many hours on this. All right, and by the way, don't forget that it's a mesh. So this is a square flag. It's too square. We are going to create a flag. A flag is more like flat like this. What we can do to make it flat? Well, because we are using shaders, maybe we can do something like, don't do it, just follow me on that. Model position Y, because we want to flat it like that. Multiply by 0.5 maybe. Yeah, it's working. Wait, we are using a vertex formulas, but we can still transform the mesh. Get back to the mesh. Don't forget that you can still rotate, change the position and stuff like that. The waves animation is not possible without our custom shaders, but if you want to move things or scale things, well, you can just do mesh, scale Y, and we're going to do 2 divided by 3, which should be a nice ratio for a flag, I think. Again, so it's scale, so mesh scale. As you can see, we get a flag. All right, don't forget that you still have access to position, rotation, scale. Let's move forward and let's continue with the uniforms. It's not that complicated, but still I want you to really understand this part with a slightly different case. We are going to send a color. For now, we've been sending the frequency and the U-time to the vertex, but as we said in our drawings over there, we can also send uniforms to the fragment, and we are going to do that right now. So we are going to send a color in order to control the color of the flag from the JavaScript. So let's go. I add a new one. The order is not important. U frequency, U time, stuff like that. U color. So as always, I use U instead of just color, which might result in a bug if you use just color, because it might mess with the color attribute. So be careful of that. It would have worked, but anyway, let's put a U to be sure of that. And the value, and this time we can provide a vector 3 with the X being the red, Y being the green, and Z being the blue. We could do that, but instead we are going to use 3 color. And it's just going to be easier because in here we can provide something like orange or an hexadecimal code that looks that looks like something like I don't know, something like that. All right, with one here. So it's just easier. Instead of providing a vector 3 to get a color, we provide just a 3 color. I'm going to use orange because I like orange. Yeah, you've seen my portfolio. So let's move forward. We save. No error. As always, just save to make sure that there is no error. We don't want to update it. We could have updated it in the .UI, but we've seen that already. So we are just going to jump to the fragment GLSL file, and we can fetch the uniform value by doing uniform, singular. And it's going to be not a color or stuff like that. At the end, it's a vector 3. All right. We send a color, and this color will be converted to a vector 3 inside the shaders. And we call it color, just like the name we chose in the material uniforms. And instead of using those, we want to use this one. Be careful, this is a vector 3, it's just RGB. We don't want to play with the alpha. Maybe we'll play later with the alpha, but right now we don't want to play with it. So we're just going to use the RGB for the first 3 values of the vec4. All right, this will return RGB and 1. The RGB of the U color and 1. You save and you get the orange color. It's that easy. Maybe we can play with cyan and we get cyan. Choose the color you like the most. I like purple too. This one is strange. Maybe there is a better one. All right, I'm going to keep the color. Anyway, we are going to get rid of it. And we are going to apply a texture. All right, it's almost the end. It's not that hard. We can just follow and discover how to use those, and we are going to practice later. So how do we load a texture? There is no surprise here. We are going to simply use the texture loader to load a texture. I think it's a texture flag inside the static folder. So, oh, my bad. Static textures. Yeah, it's a French flag, but you can use your own flag. Just keep in mind that you need a power of 2 resolution. You know why? It's about mip mapping. Get back to the previous lessons if you need. So yeah, take your own flag, do whatever you want. I'm going to use this one. All right, let's load this one. So no surprise here. We do flag texture equal texture loader, and then we load, following the path from inside the static folder. So it's just textures flag French.jpg. Let's just make sure that it has been loaded well. Yes, no error. I did save and it did refresh. Looking great. And then we can send it. Good thing, there is no surprise here. You just get to your material uniforms and you add a new one. As always, I will start with hue something, it's going to be texture. You can send multiple textures to the uniform. There is no restriction about that. We just want our pictures to be visible on it, so it's going to be hue texture. And don't forget that you have to provide an object with a value property and put the value in here. So for us, it's the flag texture. You just save, no error, great. If you have an error, just pause the video, fix the error, and get back to us. This part is a little harder unless you understood something we learned before. So we have these textures, this one. We are going to pick the pixels of the colors on that texture in order to colorize this flag. To pick inside so it's going to be inside the fragment shader because we want to change what we see in the fragments. To do that, we need the textures 2D function. So let's do that. We're going to do, let me check, what's the name? Texture color. All right, sorry, I went a little further. I'm going to do vec, maybe 4, maybe 3, I don't know. I'm going to call it texture color. Oh, first you have to get the texture. So it's going to be, sorry, I'm going too fast. It's going to be sampler 2D. This is a very specific type for textures. I know it's not called textures or image or stuff like that. It's called sampler 2D. This one is really easy to forget. I'll repeat again. Sampler 2D is the type for textures. And obviously the name is not hue color, it's hue textures. So we get our textures, these textures. Now we want to pick the color from these textures to colorize our flag. To do that, we're going to create a vec4. Why vec4? Because RGBA, which is great because that means that you can have textures, PNG textures with transparency and get this transparency inside of the fragment. There is no restrictions here. So we are going to call it texture color. And to pick the color on it, we need to use texture 2D. And the textures 2D need 2 parameters. Don't forget the semicolon. The first parameter is the texture. So it's this sampler 2D that we created and added here. So it's this one. It's hue texture. It's just a 3GS texture. So this is the first parameter of texture 2D. And the second parameter is where on that texture we want to take the color, to pick the color. Like if it's this part, we want to take this part. If it's the corner right here on the top right, we want to take the color here. Do you remember about this? We are talking about UV coordinates. All right, these are the UV coordinates. We could have created our own coordinate and send those to the geometry in the attributes, stuff like that, but it already exists. Don't save the fragment. Just look at my screen. I'm going to do log geometry attributes, and you'll see that there is a UV attribute in here. And these are the coordinates of the texture on the geometry to place a texture on that geometry. All right, remember when we unwrap things just like a candy or stuff like that? This is the same here. It's 2D coordinates on where to pick the color on an image to put that color on the geometry. So let's use this one. The problem we have here is that we cannot access it inside the fragment. Remember that in the fragment, so here, we cannot access attributes. What we did to get the attributes from the vertex to the fragment, we use varyings, and we are going to do that now. So we get, because it's inside the geometry attributes here, we can access it from the vertex, and we can do vec2 UV, right? We get the UV. I know it's not a UV because it's a native 3GS, so we cannot choose this one. We could have renamed it, but it's far-fetched. And what we are going to do now is send this one. We are not going to use it inside the vertex. We want to send it to the fragment. So we are going to create a varying singular. It's the same type, so it's a vector2, and I'm going to call it VUV. All right, you cannot call it UV. You have to change the name, and I use V for varying. And then here, you can just take the UV value and put it inside the VUV. You can save. You will get a warning telling you that, all right, there is no error, but you are creating a varying and not using it in the fragment. What did I change here? Oh yeah, nothing important. It was just the log. Then in the fragment, you can get this varying. So we are getting the value we are sending from the vertex to the fragment. And to do that, we just write the same thing. So varying vec2 VUV right here. The order is not important, but I always put precision, uniform, varying. And if there are attributes, it's a precision, uniform, attributes, varying. It's just a logical order, but you can mix the order. It will be the same. We save. It's not working. And maybe it's because we are not using it. My bad. I said VUV equal VUV. So VUV, the varying, equal the UV. Sorry for that. So in the texture UV, we are going to use the VUV. Sorry, I messed this one. Anyway, right now we are sending the UV to the fragment by using a varying VUV. We update the varying here with the same value. We just take the attribute and send it to the VUV. This value will get interpolated. All right, so between those vertices, we will have interpolated values. And in the fragment shader, we get it from here. So VUV, it's the same declaration. So varying vec2 VUV. And we use it as the second parameter of texture.d, meaning that we are going to pick the textures, the colors on the right position inside of it, because the UV of the plane is the right one. So right now we don't get any difference because we are not using that texture color. We did pick the right color on the texture, but we are not using it. What we need to do now is use this textures color on our GL frag color. And because texture2d returns a vector 4, even if the alpha is 1, well, we can just use it like this inside the GL frag color. And we get our flag looking great. All right, this is the way of using textures. It's a little far-fetched, I know, but it's almost always the same thing, so you will understand it after some practicing. All right, great. Texture2d returns vector 4. Let's add some color variations because right now it looks like really flat and not realistic. What we are going to do is add more brightness when the vertices is high, so close to the camera, and less brightness if it's in the depth, so that we can like mimic the shadow. It's not physically correct, but it will just add some relief on our flag. So first what we are going to do is move to the vertex shader, and we are going to send the elevation. So I know it's toward the camera, but we can still call it elevation. We are going to save it inside a variable and then send it to the fragment. And using that elevation, we are going to update the color, make it brighter or darker. So let's go. So this is the elevation part. So we are going to put it inside a variable. Follow me on this one. It's a little harder because I need you to struggle a little in order to learn. We don't really need this part. There is nothing new, but it's just harder, which is why I want to do it. So we are going to call it elevation. It's a float because it's just like a value moving on the Z. And I'm going to put the first part here, right? It's the elevation. Don't forget the semicolon. And then I'm going to add the other part, right? It's just the waves on the X and the waves on the Y. So elevation plus equal this, this part, right? I'm just saving what I'm doing here inside a variable. Then I will use that variable to update the Z, all right? It's exactly the same, but I'm first creating a variable containing the elevation, and then I'm using this variable to move the model position on the Z. We get the same result. But why did we do that? Well, it's because we want to be able to send this value to the fragment in order to create those brightness and darkness. So let's go. We are going to send something to the varying. So we are going to do float v elevation like this. So I created the varying. I can update it here. I'm going to do v elevation equal, and I can just take this value like that. There is many different ways of doing that. Maybe you find a better way. Anyway, do what you want. So I'm sending it to the fragment. I get the warning telling me that I'm sending varying but not using it. That's true. Let's get back to the fragment. We can retrieve it by using varying float, because it's a float. It's just one value. It's not a vector 2 or something like that. V elevation, like that. So we get this value, but we are not using it. And then with it, what we can do is just play with the texture color in order to change the color. And we're going to crank the value up if there is an elevation, and crank the value down if there is an opposite elevation, like it's going deeper. And actually, because we are using sinus on it, it goes something like from 0.1 to minus 0.1. Just trust me on that. Sinus goes from minus 0 to minus 1, to plus 1. And because we are multiplying by that value, well, it goes from minus 0.1 to plus 0.1. Maybe you didn't got this part, but anyway, just try the values and we'll see if it works or not. And maybe we just multiply it so you can see it better. I usually just do that. And we're going to multiply all the channels of the texture color, but not exactly. We don't want to change the alpha. All right, we don't want our flag to be transparent in the middle or something like that. What we want is to play with the R, G, and B only, and to multiply them up or down. So to do that, we are going to use texture, color, and only target the RGB. We don't play with the A. We could have write X, Y, Z, but because we are managing colors, well, let's call this RGB. And we just multiply by V elevation, like this. But be careful, we multiply by something that can be negative. You can just test if maybe we see a result. Yeah, we cannot see much, but because it's very close to 0. So first we can just multiply it, I don't know, let's say 2. We can play with it, all right? But because it can be negative, positive, we get this strange result. Well, just add some to it, and to add some, well, you just add, I don't know, 0.5. Yeah, it's 0.5, and we get this. And if you're not happy with it, well, you can crack it up, I don't know, 0.9, we get something like that. You can do whatever you want, and you can even send uniforms and add those uniforms to that GUI and play with them. All right, we are done with the flag. Yet again, send me your flags. I want to see use your country flag. Just search on the web for your flag and add it and toggle it and play with it. I want to see what you're doing with that. All right, that was long. It's almost the end. What we are going to see now is the shader material, because we used the raw shader material. I told you about the shader material. It's the same, but with pre-built uniforms, attributes, and precision prepended to the shader codes. All right, we have some of those codes already inside of it. It will be prepended, so we can just get rid of part of this code. It's just slightly faster to write shaders this way. So first, you need to replace raw shader by shader material, and we are going to get an error, because you can just read the thing here, the error, projection matrix redefinition. Right now, WebGL and 3GS are telling us that we are redefining this variable. And yes, because it has already been prepend to the code. So we have to get rid of everything that is doubled. We can get rid of projection matrix, view matrix, model matrix, position, UV, and the precision. So let's go. This one, go. View matrix, we don't want it. Model matrix, we don't want it. U frequency, it's ours, we keep it. U time, we keep it. Position, already sent. UV, already sent. I'm just watching these things. I save, yeah, looking better. And we can also get rid of the precision. It didn't trigger an error, but still we can get rid of it because it will be prepended. And yeah, now it's working. Great. And that's all for the shader material. We don't need more, it's just some code being prepended so that we can start coding. I don't recommend using it when you start, because I've been using it the first month and I was like, where those matrices come from? I just could not understand where those matrices come from. I should have spent more time in the documentation. Anyway, no judging. So let's talk about debugging. Yeah, first finding errors. And we did some errors, and you probably did some errors too. Let's say we forgot a semicolon. We get nothing on the screen because the material doesn't work. The rest of the scene might work, all right? But the flag will not work. And we get an error, and we can just read the error. 3GS and WebGL are doing a great job just to providing you the error information. Just read it, and you might find what is right. Here we can read error on line something like 063 void syntax. And this is a problem because the error is on the line 63. But this is not the line 63, it's something like, I don't know, it's less. But this is because we are using the shader material, and the shader material prepended a lot of things inside. So instead of trying to find the line here and it's not right, just scroll and you will see that on line 63, this one, yes, there is a problem. Remember, we forgot a semicolon here and we get an error, and that's true. But the error came from the following instruction, because when you forgot a semicolon, sometimes it will trigger, most of the time, it will trigger an error on the next thing. So just search for this number. So it's 63. Search for it. All right, it's void main, so it's this part. So it's exactly the same thing. We just have some code prepended. We don't care about it right now. And then try to find the mistake you did, and it can be right before. And indeed, we forgot a semicolon. In the end, just read the error. Yeah, by the way, as you can see, when we do a mistake, you can read the whole shader, and it's really useful if you're using shader material instead of raw shader material, because you will learn everything being prepended to your code. And as you can see, there is something like 50, maybe 60 lines of code, whereas things about morphing, use color, and as you can see, there is a position, the UV, also the normal that are already sent. So these are the attributes. And we have some uniforms like the model matrix, model view matrix, projection matrix. We've learned about those. All right, so just do an error and you will be able to read this. There are plugins and stuff like that that let you read the shaders, but they don't always work. So be curious, try plugins, Chrome plugins, maybe computer apps that let you just see the shader code, but they are not very stable. So I won't recommend any one of them. Still be curious. So yeah, just you can read in the error what is inside the shader with the shader material. So if we cannot log anything and print anything, how can we test values? Well, this is the hard part when you have to just find solutions. And usually what we do is just we send the value to the GL frag color in order to see something. So get the semicolon back. If I want, let's say, to know what's inside the VUV or something inside this vertex. If it's inside the vertex color, I won't be able to see it on the fragment, to see a color. So I will have to send it to the fragment by using varying. And I'm doing it with the VUV, and you can check the VUV just by sending it to the GL frag color. And I can do it after. I don't care if I already set the frag color, I can change it after. And do GL frag color, vec4, and I use the VUV and use 1.0 and 1.0. This way I will be able just to test this value visually. Now we get that. And then I can see that, oh no, this is wrong, it's not supposed to be like that, and I will have to understand what I'm seeing and what is wrong. All right, so you can just show the values on the plane by using the fragment color and changing the GL frag color. It's hard, it's harder, but there is no other way. I mean, maybe there is other way, but this is what most people just use. And this is it. That was a long one. That was probably the longest one. Still, it was huge, and I hope you did understand a lot of things. As I said, we are going to practice, so you're going to be fine. If you didn't catch everything, we're going to just practice and learn again. Your first shaders will take countless hours. And as you can see, we start to use mathematics to do something like waves and stuff like that. And we will do some mathematics. I'm bad at math. Still, I can manage to do those things. So you will be able. You're probably better than me in math. I really, trust me on that. I'm really bad at math. And still, I manage to do things. So you will be fine. Don't worry. But it will take time. It will take hours. You will do a mistake. You did just, I don't know, you put 0 and it's not working because you forgot 0 point something, and we spend an hour searching for it. And just do some searches, go to Stack Overflow, just search, use the 3GS community, the 3GS journey community, and we are going to help you. And also study the existing shaders. All right, there is many examples on the web, many examples on the 3GS website, but you can also study the 3GS shaders. Just go to the node modules, find the shaders. We will do that together, but you will learn a lot. They are very complex, but sometimes we'll learn a lot. Anyway, I put some links. As always, here there is only 4 links. If I find new more, just check the links panel and I will add them to the links panel. So there is the book of shader. This one I will talk a little about it. It's just great. It's about fragment shader. It's about like drawing stuff. It's not about positioning things in 3D, but still you will learn a lot in this one. All right, so check this one. It's not finished, but still it's really great. The first part, you will learn a lot. Then there is Shader Toy. This one, if you're a beginner like me, you probably don't learn a lot from this one because it's too complex and you can see crazy ass stuff. Let me check if I can just give you one example. From the popular one. Oh, this one's just crazy. All right, this one. Quick preview. I will keep it small like that, so sorry you cannot see much, but my computer won't like it if I increase it. Just go to the shaders, watch those. These are shaders. It's not 3GS, it's just shaders. And those guys they can draw mountains, people, stuff like that, just by using shaders. No 3GS, no buffer geometry or stuff like that. All right? I won't be able to understand what's happening here, so it's a lot of code. But anyway, you can check those, and if you understand, well, you're a genius. There is the Art of Code. It's a YouTube channel, and there is Lewis Lepton. We talk about this guy. Just check those. They are great, and I will add more links if I find some. Also, one last more thing. It's about GLSL EFI. Maybe you know about this one. We are not going to use it anyway. I just want to talk about this. With GLSL EFI, we can import and export GLSL code just like modules. Like you can write in another file just a small part, like a function, a GLSL function, and then inside your vertex shader, you can import just this function. All right, this is just like modules when you have multiple files and you import them and then instantiate stuff like that. You can import just part of code inside your shaders, and it can be great in order to reuse things and to separate in small chunks. It's more manageable. We're not going to use it because I want to keep things a little simple though, but you can use it by using the GLSL EFI loader and add it to Webpack. All right, and that's all. I hope you learned a lot, and we are going to practice in the next lesson. See you there.